So we are asked, does this series diverge or converge? That's what we're asked. Now the first thing that you should always do when you have a series is do a divergence test. So let's do a simple little divergence test. Basically take the limit of the sequence of all of your sums, okay, at infinity. So what is the limit as n approaches infinity, or 7 over n plus 1? Well, notice that when we evaluate this, this is going to be 7 over infinity, which will simplify just simply to 0. So when we get a result of 0 from the divergence test, what that says is this is an indeterminate, okay? We can't really say for certain if our series is divergent or convergent, right? So it doesn't really tell us much. I just thought I'd point that out because this should be the thing that you always do first. Any series that you can't find the sum of easily, or know that it's like a geometric or harmonic or a p-series, do the divergence test. It's going to save you a lot of time. Okie dokie, so we can't use the divergence test. I suppose we could use the integral test, but that's going to get long and tedious. Let's do a comparison test, right? That's what this problem is context of. We need to do a convergence test or a limit comparison test. So I'm going to go ahead and do a little comparison here. So I'm going to say that 7 over n plus 1, right? I'm going to notice that this is like n squared plus n, so I'm adding something every time. Well, I can make the relationship that 7 over n squared is something. Okay, hopefully you see it. There's the highest power here is n squared, but you're adding an n thing here. So if it was n to the 1, I'm adding 1, I'm adding 2, I'm adding 3, I'm adding 4. So I'm going to make this denominator greater every single time than I would with this one, because this factor is the same, but we're adding an n every time to that, right? So we're going to say that this is greater, and the way that you can see this is distributing n squared plus n, right? The n squareds are constant, but we're adding n every single time, and that's going to grow the denominator, and actually that would make this one greater. Oops. Right? Because if we grow the denominator 1/2, 1/3, 1/4, we get lesser, less, lesser, least. Okay, when we go this way. And that's what we're doing here. So this will be true. Now if you feel like proving that, we could simply divide over this. So we could say 7 over n squared plus n is over 7 over n squared is less than 1. We could reciprocate everything to say that this is n squared over n squared plus n is less than 1. You should say that this is true, because for all of these terms we plug in, we add more. It's always going to make the numerator less than the denominator, which is always going to output something less than 1. So this is true. We know this. So we're allowed to make this statement that 7 over n squared plus n is less than 7 over n squared. Let's use this ideology to solve. So what do we know about this series, right? The series we're comparing to. Well, notice that this is what's called a p-series. Some constant over a variable to some power, okay? And that power could be variable, but in this case it's not. So we have just a simple p-series. Now, when this exponent is greater than 1, we know it's convergent, because we're going to grow the denominator and grow the denominator and grow the denominator and grow the denominator. And as we reach infinity, well, the limit as this approaches infinity is 0, so we're going to converge to a single point, right? So because we know that this is convergent by p-series, does it tell us anything? Let's make a little graph here. So I'm going to make this function, or this series green, I'm going to make this series blue. All right, let's think about it. 7 over n squared, what's happening there? Well, this one's greater, and it's going to converge to a point. Okay, think about it kind of like a function. It's going to converge. But all the values here, I don't care what the graph looks like, by the way. I'm just trying to make a point. This graph is always greater than this one, or this function. So knowing that, and it converges, it's going to go to a single point. Let's say it's decreasing to a single point. Well, here, we know it's always going to be less than, so it's always going to follow under that curve. So what this tells us is that, okay, if this is converging to a point, it's going to squeeze this function to also converge to a single point. It can't go above that line, so it can't just diverge into infinity. No, it's going to follow and converge somehow underneath or equal to this function here, or actually less than because we're adding n. But you get the point, right? So we're going to say, for our answer, because 7, the series 7, infinity, n equals 1 over n plus 1 is less than the same series but without that plus n factor. So 7 over n squared. And 7 over n squared, that series, is convergent. Our initial series must also converge. Okay, so here's our logic, right? Basically, as a recap of what we did here. We have a series, we don't know if it's geometric, harmonic, blah, 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 blah. Not really determinate. We take the divergence test. We find that to be indeterminate. We say, okay, we could do an integral test, but we could also just do a comparison test. I noticed that this is always going to be greater than our initial series. So I identify it as being convergent because it's a p series and the exponent is greater than 1. I'm going to use this logic to say, okay, well, if this is true and our p series is convergent, well then our initial function must also be, or our initial series must also be convergent. I hope that you found this video helpful. If you did, please drop a like, comment, and subscribe, and I hope that you have a wonderful day.